Welcome, ladies and gentlemen. Actually, I was going to say I'm Professor Krause, but you all know that. Professor Mahoney and myself are proud to host this year's senior capstone presentations. As you know, a capstone is intended to reflect the sum of what a student has learned during their time here. And we believe that this year's graduates have met both the spirit and the letter of that, and we are very proud of their accomplishments. And with that, I will present Kevin Krause.
Thank you, Professor Kowalewicz. Thank you for coming, everyone. My name is Kevin Krause, and today I'm going to be telling you about my thesis called CHEMBERRY. So when we were given the task of coming up with a thesis project, we were asked to solve some problem that we had observed. And as some of you may know, I used to be a chemistry major, so I've taken a few lab classes at Carthage. And something I've noticed is that when we have to use software as well as doing the experiments, that can be kind of a hard thing to grasp. Mastering two things at once isn't easy. So something I've set out to do is improve the experiment process. So how can we simplify this process to make it easier for students? And I also want to highlight that the overarching goal of this project is to make the experience for the students easier and better. So in doing this, I have a few questions that I need to resolve. So I know I want to use some type of microcontroller to do the data handling, but how am I going to collect the data with it? I also want to provide a way to share the data with the instructor of the lab class, so I want to find out how to send the data to another device. I also want to find a way to summarize the data. So if there's multiple classes doing the same experiment, I'd like to show if there's any difference between the classes and what those differences are. And finally, some experiments it's not easy to tell what's going on just from looking at your data. So if you're doing a titration, for example, you could see the titration curve. So I'd like to provide a way to visualize the data as well. And lastly, I want to make sure that whatever I create, it's scalable for future work. So if someone else decides to build off of this in the future, or I decide I want to add more sensors, it's easy to do so. And here are some devices that already do this type of thing. So the one we use at Carthage is called the LabQuest 2. And as you can see, it's a pretty complicated interface. There are a lot of buttons and a lot of features, and it's kind of overwhelming for someone that's just in Chemistry 101 or something. So I think it's too cumbersome for our purposes. Not to mention, it doesn't have Wi-Fi capabilities. Those have to be bought. So if you wanted to share your data with your professor, that would not be easy to do. So if you wanted something simpler, there are other types of devices, such as this one. And while they are much simpler and easy to use, they're kind of useless because they can't do much other than just display the data. So I want to find something that can compensate for the shortcomings of both of these products. So here are my objectives. I want to expedite the data collection process, and I also want to relieve the instructor of all of their tedious tasks that they have to do during the classroom so that they can really focus on the students that need help. I also want to encourage electronic note-taking, so you no longer have to have a really sloppy lab notebook. Everything's recorded on the CHEMBERRY so that you can go back to it, easily see what you've done, and do whatever you want with the data. And as I want to find a way to easily share that data between the instructor and student. At a glance, this is the flow of the program, and there are actually two programs running. This is the one that's running on the student's CHEMBERRY, and there's a separate one that's being ran by the professor on their machine. So on the professor's machine, they will select an experiment. This is optional, but they will select an experiment that they're doing in the class that day. And that experiment will be broadcasted to all of the students in the classroom. Once the students know what experiment they're conducting, they can choose the devices that are appropriate for the experiment. So, for example, if you're doing a titration, you'll need to use a pH sensor. And once the instruments are selected, you can actually begin to do your data collection. And it's very simple to do. There's one button you press, and once you press it, all is said and done. And as the data is being collected, that is automatically being sent to the instructor so that they can constantly see what you're up to in a good way. And if they see that your results aren't what they're supposed to be, they can maybe come and help you out or correct whatever problem you're having. And this cycle continues throughout the whole experiment. So the two major components to this project are the software and the hardware. So I've listed out what the software does and then the hardware that corresponds to whatever that feature is. So the software will collect data, and the piece of hardware that does that is the Arduino. And the software will present and send and summarize the data, and that's being done by several chemical sensors which are attached to the Arduino. And lastly, the software runs on a Raspberry Pi, and that's not the instructor's software, that's actually the student's software. And the instructor's software can run on any machine. And when I actually set out to doing this, the development process was a little like this. So my first step was to talk to the people that would actually be using this, such as chemistry students, and finding out what they specifically dislike about the lab quests or whatever other software they've been using. And once I knew what they really wanted, I set out to pseudocode. And if you don't know what that means, it's basically outlining the structure of your code. So if you're writing an essay, you usually outline it before you actually get to the specifics. And once I had a general structure of what I wanted to do, that's when I started the well-known process of building a little and then testing a little. So I would build the code that does the pH sensing, and once I had finished that code and ensured that it worked, I would show the results to the students or whoever I was asking for the requirements and see what they think of it. And while I'm only working on this portion of the code, I can also isolate bugs. So once I've determined that this part of the code's good, I can move on to the next one. And I'd repeat this process until I'd finished everything, put it all together, and have a working thesis. And speaking of those requirements, there were two major things that people were seeking. The one that I heard over and over and over again was some way to make the Excel work easier. So in some classes there's an overwhelming amount of data, and doing all the number crunching in Excel is a waste of time because it's not contributing to what you're learning in the class. So one feature would be to expedite the Excel process, do all the statistics for you, and make that a lot quicker. And the second one was a troubleshooting feature. Some of the instruments that they use in the chemistry labs, such as maybe the IR or the NMR, they're pretty complicated machines, and unless you get everything right, they're not going to work. And usually you don't know why they're not working, they just they don't work. So I wanted to find a way to show that if something is going wrong with the software, it tells you exactly what you need to do to fix it. In the classroom, this is what the situation is. So there are usually 7 benches in a laboratory, and there's one at the front of the room, and then there's 6 in the back, and the one at the front's where the instructor sits. So each student or each pair of students, because usually experiments are conducted in pairs, each pair will get their own CHEMBERRY. And once the instructor has set up the experiment, the CHEMBERRY'S are all constantly sending data to the instructor. So the instructor doesn't have to weave around these really tight tables. They can simply survey the room from the front, look at their program, see what's going on, and if all's well, they can continue sitting there. But if they see that there's a problem, they can go specifically to that student and help them out. And let's actually show how this works. So I actually have the professor's GUI on the left, and I have the student's GUI on the right. So right now there is no experiment, so I'm going to go ahead and select one. And I've already prepared one, so I'm just going to go find it. So for example, we could do a titration experiment. So the objectives in the abstract are shown here. Here's what the students will see. I actually copied and pasted this from the current lab manual, so it's a little bit verbose, but you could probably put very succinct phrases and sentences in here that would fit on the screen. Here are the materials required, and here are the sensors that the students ought to use. So I'm going to hit finish, and then I'm going to hit broadcast. And the student gets this message that says the instructor has sent you an experiment. So if I hit experiment details, I can see what the experiment is. So let's say I want to first take the temperature of my solutions. So I hit configuration, and then I selected the temperature. I'm going to hit finish. So the ambient temperature of the room, it's a little bit warm because I'm really warm right now, and it's about 24 degrees Celsius. But if I actually hold this, it'll probably get a little bit warmer. And I'm going to hit measure a few times, and what you're going to see is that it's going to save the data points in this column, and then it's going to automatically appear over here. And when I was talking about summarizing the data, you can have some statistics right here that show the average of all the points, the standard deviation, which there is none because there's only 1 point. So you get the idea. And let's say you were doing a titration and you wanted to see what the curve looked like. So you can click Visualize. And, oh, I know why that's happening. What that would do is it would show you a plot of the x-axis being the points and the y-axis being the values. And once the students close their side of the program, the instructor's side will show that change. So this student has gone away, and it will actually automatically save their results local to this machine, so that if the student somehow loses their data, the instructor still has it. So in assessing this project, I'd like to go back to the questions quickly and remind us of what I set out to do. So the first thing I wanted to do is I wanted to collect the data. And the second thing I wanted to do is I wanted to be able to send it to another device. The third thing I wanted to do is I wanted to summarize it and provide some very basic statistics on it. And lastly, I wanted to be able to visualize it. And I also wanted to ensure that the way I build and structure the code, it's scalable for future work. And here's a summary of what I actually did. So I created a simple GUI that streamlines the data collection process. I was able to reduce the instructor overhead by allowing the instructor to stay at their front station and simply survey the results of the class just by looking at their screen. I simplified the experiment design process just by allowing instructors to type in the text boxes or select something they had already written and sending that. And ultimately what I've accomplished is a method to allow students to customize their laboratory experience. So whether you're in a class or you are researching with another instructor, you can tailor this to whatever you're doing to make whatever type of chemistry work you're doing much easier and efficient. So in thinking about everything that's happened thus far, it's been pretty cool seeing a software project go from the beginning of its life cycle to the end. And obviously it's not finished, but there's always things I can improve and there's always things I can add. So that was a pretty rewarding experience. And I also learned a lot about what I'm good at and what I could work on in my software development skills. There's always something to learn. And I wanted to include this quote by Dijkstra, who's a famous computer scientist, because I think it really captures what we do. So computer science is no more about computers than astronomy is about telescopes. So to me, that means that this type of work is about the methodology and it's about the algorithms. And while it does involve hardware, it really is about solving problems using computers. And I think that's pretty cool. So with that, thank you for listening. Does anyone have any questions?
I guess, do you think about any features that you were thinking about adding to the project as you were writing it, and what were those features that you wish you could have added if you had time?
So I would have liked to interface it to like the IR machine. In the IR, you put a chemical in and it kind of prints out a graph of its composition. And that would be kind of a complicated process. So I thought I'd just start with the easiest instruments to interface with. But I think the way I've written it, I could definitely generalize the sensors so that I could include something like that, or whatever. I saw Lesia first.
What were some of the challenges that you faced during this project?
So primarily my challenges were getting the data from my Arduino to my Raspberry Pi. There are a bunch of technicalities that I had never dealt with before, because everything I've done until now has just been purely software. So when I had to deal with like the bit rate going from the Arduino to the Raspberry Pi, and knowing how to convert the voltages, and that it was a huge learning curve. So that was definitely the hardest part of this project.
Can you talk a little bit more about, you were talking about the different sensors that you could plug in. So what has to happen, let's say I invent a new sensor, what will that mean to your software? Is there some like inheritance you could take advantage of, that all the sensors have something in common and you could just plug this into your system?
Yeah, there is. So one of the things that I was really trying to nail were the design patterns involved with this project. So I used the strategy pattern to accomplish things like that. So various sensors have different responsibilities that they need to carry out. So they all inherit from a single class. And should I choose to add a new sensor, they can inherit from that class. And then the GUI that actually tells the sensor to take a measurement, that method is abstracted into that parent class. So if you were to add another sensor, as long as you know how to convert, as long as you know how to read it from this board, then it would be pretty easy to do that.
Do most sensors just kind of produce numbers at every fixed points? Or are there some sensors that do 2 numbers or 10 numbers or 100 numbers? Or?
So these sensors will produce a value about every second.
Just a single?
It's a floating point number. And off the top of my head, I can't think of any that continually produce numbers. You can tell it to report the numbers as frequently as you want. But I found that if you tried to measure it really fast, you'd start to get some very strange results. So I think by having that fixed interval, it's more accurate.
And then one more question about the patterns. Communication between the student machines and the instructor machine. So I'm guessing you use the proxy.
Yes. Yes.
How many of those devices do you have to actually test it? Did you try actually having 12 talk to a?
I tried to do about. I did 3 at once, and that worked, and it was. There didn't seem to be any lag on either side. So this could definitely work where there's 12 machines in a classroom and 1 instructor.
And did you use Java or Python? Or?
Yeah, I used Java primarily for the GUI, and I also used C++ for the Arduino because the Arduino has to be in C++. If I was to change something, I might not use Java, because as I got further along in the development process, I found that the amount of classes I had to deal with started to become very overwhelming. So that might just be something I need to learn to become better at, is just the object-oriented programming, but it's something I would consider, is changing the language. Yeah?
Moving on from you said, what language might have made it a little bit easier?
I think I would have done it in a low-level language like C++ or Rust, just because it's easier to do the low-level stuff, and there's low-level stuff involved. So that's probably what I'd attempt to do.
Did you have to make any changes for like the workflow or pseudocoding while you were making it? Like, was there any part where like, what part of the workflow
So like as I was pseudocoding, did I determine that something wasn't going to work?
Yeah. Or back when we had that slide.
Yeah, so there was a time when I was considering allowing you to save your results on Google Drive. So for example, you're doing an experiment with your partner. I wanted to find a way to save the data to the cloud. And I had almost started the step 3 building a little and testing a little with the Google Drive, but I found that that API was a little bit, it would get in the way and I'd end up having to spend too much time on that. So I just decided to stick to saving locally to the hard drive. So when you notice something like that, it's important to be able to predict, is this going to fit in the amount of time I have? So that did happen a few times. Yeah.
You said the user experience for existing devices isn't great. Do you have any evidence that the user experience on this system is any better? And how would you even determine something like that?
So I did show, so originally I had so I'll bring up, actually I closed it. So the first GUI I developed was very primitive. And when I showed that to some of the chemistry students, they liked its simplicity, but they flat out said it was ugly. So I had to redo the GUI. And once I showed it to them, I just allowed them to kind of play with it a little bit. And they preferred it exceedingly to the LabQuest. And if I was actually going to see how this would work, I think I would have some of the students that work in the summer actually, they repeat the experiments to make sure they work. So I'd have them use this instead. And it's simple enough that I think I could just leave it in their hands and they could tell me if it's easier or harder to use.
Okay, thank you.